Hello everyone, I'm very honored to introduce our work to you in this video. We are from Department of Electronic Engineering, Tsinghua University. The title of our work is Named Entity Recognition in Multi-Level Contexts. Named Entity Recognition, or NER, is defined as automatically identifying and classifying named entities into specific categories in text, for example, person, location, organization. It is a critical task in natural language processing and a prerequisite for many downstream tasks, such as entity linking, relation extraction, and question answering. NER is usually modeled as a sentence-level sequence labeling task. In previous work, many neural network methods were applied to the sentence-level NER task. The BiLSTM CNN-CRF model is a typical example. They employed CNNs to capture morphological word representations. Then they used LSTM to capture sentence-level context, and CRF to model the dependencies between adjacent texts. Recently, the context-sensitive representations captured by language models were proved to be useful in NER systems. TAG-LM was first proposed in 2017 to introduce LM embeddings in this task. Afterwards, ELMO and BERT were proposed for better contextual representations, and they all reached higher NER performances. To combine context beyond sentences, several methods were proposed to mine document-level information, such as global attention and memory mechanisms. However, existing methods suffer from several problems. First, the performance of sentence-level methods recognizing entities in limited or ambiguous contexts is usually unsatisfactory. Second, existing document-level methods ignore the sequential characteristics of the sentences within a document, which may be suboptimal. Finally, most previous work ignored the word's preferences of entity type and relative position from the entities. Our work is motivated by the observation that the contextual information beyond sentences can mitigate the negative effects of the ambiguous and limited sentence context. The sentences within a document are highly related, and the interactions between them can provide document-level contextual information. Besides, words themselves contain preferences of entity type and relative positions from the entities, and the preferences provide word-level contextual information. For example, in this figure, sentence 1 is ambiguous because it can be either his mother called Elizabeth Trump or a business called Elizabeth Trump and Son. But another sentence in this document explicitly mentions Elizabeth Trump and Son as a company's name and solve the ambiguity. Besides, the sentence 2 in this figure has limited context, and the word said can easily mislead the classification of the type of coal ink. However, the multiple mentions of ink in other sentences indicate its preference to appear as the last word of organizations. Thus, these preferences of words have the potential to help recognize entity types more correctly. Then we will introduce our approach in detail. First, we introduce our baseline model, TAG-LM. It first captures character-level information of words, because named entities usually have specific morphological patterns. For example, China with the capital letter refers to the country in most cases, while China without the capital letter mostly refers to porcelains. Therefore, TAG-LM learns character representation CK with a two-layer BiGRU. Then character representations are concatenated with the word embeddings WK. They are then fed into a two-layer BiGRU to learn context-sensitive word representations. We denote the output of the bottom and the top BiGRU as H word and H sequence. Finally, H sequence are fed into a CRF layer to predict the tag sequence. Next, we will introduce how to capture and fuse document-level context. First, we obtain the context-independent sentence representations. Since each word in a sentence has different importance, we apply the neural attention mechanism to filter the uninformative words. Then we contextualize these representations with a sentence-level BiGRU. Next, we propose to capture the interactions between sentences with the multi-head self-attention mechanism. In most existing attention mechanisms, a sentence's attention weight is only based on its representation, and the relationships between sentences cannot be modeled. Self-attention is an effective way to capture the interactions between sentences. Besides, a sentence may interact with multiple sentences. Thus, we propose to apply the multi-head self-attention mechanism to learn better representations of sentences by modeling their relationships with multiple sentences. The final representation of the ith sentence, denoted as DI, combines representations of all sentences within this document. Thus is regarded as the document representation of the ith sentence. To fuse the document-level context, we first add a special token BOS at the beginning of the sentence and feed the sentence into tag LM's bottom ByteGRU to compute each word. Then we compute the document representation DI and replace each word 0 with DI and feed them into the top ByteGRU. The input of the top ByteGRU contains document and sentence-level contextual representations simultaneously. Thus, its output hidden states act as the fusion of the two contexts. Finally, we will introduce how to capture and fuse word-level context. In natural language, words themselves have different preferences on different entity types and relative positions from the entities. We encode the preferences with the probability distributions of word labels, because the label of a word indicates its entity type and the relative position from the entities. For example, BORG means the first word of an organization. To learn the distributions automatically, we propose an auxiliary word classification task and employ a two-layer network as a classifier. The classifier's input consists of the morphological representation CK and the word embedding WK. Besides, we add a position embedding PK to represent the relative position information. Then they are fed into the two-layer classifier to predict the label distribution PK label. To fuse the word-level context, we concatenate PK label with the original CRF input H sequence to enrich word representations with the label distributions. The CRF takes the enhanced word representations as input and decodes the best label sequence. During training, we use the negative log likelihood as CRF loss function for NER task, and we use PK label to compute the cross-entropy loss for the auxiliary word classification task. Our framework is jointly trained on the original NER and the auxiliary classification task via multitask learning. Next, we will introduce our experiments. We evaluate our approach on the Cornell 2002, Cornell 2003, and Wikigold NER datasets, as shown in the table. We report the official micro-averaged F1 scores on all the datasets. We use BIOES labeling scheme. For English datasets, we use the Senna word embeddings. For Dutch and German datasets, we use the word-to-vec embeddings. We adopt ELMO as the pre-trained LM embeddings and fine-tune them during training. We add 25% dropout to the input of all GRUs. We use the Adam optimizer with gradient norms clipped at 5. We train our model for 20 epochs, and we divide the learning rate at the 10th and the 15th epochs. We report the average scores over multiple runs with different random seeds. The table shows some other hyperparameters. We compare our method with previously published state-of-the-art models, and the results are shown in this table. We can observe that the incorporation of multi-level contexts brings improvement on the English, German, and Dutch datasets compared with our baseline model. In addition, our model outperforms most of the previous sentence and document level methods on the three languages. The improvements demonstrate the effectiveness of our framework, which fully exploits the document and word level context and combines the multi-level contexts. To study the contribution of the document and word level context respectively, we conduct experiments on two settings, only incorporating the word level context and the document level context, and compare the F1 scores with our model. This figure shows the results, from which we have two observations. First, the document and word-level contexts both bring improvements on the four datasets. It indicates that either of the contexts can help alleviate the effects of the limited or ambiguous sentence context. Second, the multi-level context method improves the F1 score over the other two settings on all the datasets. It validates the effectiveness of the fusion of multi-level contexts. With the assistance of more extra contextual information from the document level and word level, our method performs better than the other two settings of combining only one context. Next, we do some analysis on our method. First, we compare our way of fusing the document level context with three alternative ways, as shown in the first table. We can see that enhancing each word with the same DI for all words performs badly. We replace each word 0 with DI, and the GRU unit aligns DI into the same space as each word and produces better performance. Second, we compare three ways of fusing the word-level context, as shown in the second table. We find that CRF is more suitable to encode the distributions of word level than by GRU, because there exist strong connections between the two adjacent word label distributions intuitively. Finally, we compare three choices of attention mechanisms at the document level, as shown in the last table. We find that the multi-head self-attention performs the best, because it can capture a sentence's interactions with multiple sentences. Then we analyze how to choose the weight of word classification loss, and illustrate the results in this figure. We speculate that lambda controls the proportion of the word-level context in all contexts. When lambda changes, the balance of the context is broken, and the performance is affected. Besides, lambda controls the learning rate of the word label classifier's parameters. Its increase and decrease will hurt the accuracy of the label classification. This table shows the comparison of the baseline and our model on two example sentences. Blue, red, and orange entities indicate the names of organizations, persons, and locations. In the first case, the ambiguity of little disturbs the baseline model. Our model finds another explicit mention in this document and correctly identifies this entity. In the second case, the entity is wrongly classified as organization. Our model notices the two other mentions of ground, both of which appears as the last word of location, and corrects the wrong entity type. The examples prove that our model can mine contextual information outside sentences and recognize entities more correctly than the baseline model. Finally, I will conclude our work. We propose a unified structure to incorporate multi-level context for NER. To incorporate the document-level context, we propose to learn relationships between sentences within a document with the multi-head self-attention mechanism. Besides, to mine word-level contextual information, we propose an auxiliary task to predict the word type to capture its type preferences. Our model is jointly trained on the NER and auxiliary tasks through multitask learning. We evaluate our model on several benchmark datasets, and the experimental results prove the effectiveness of our method. These are references in these slides. Thank you for listening.